Okay, I'm going to do a tour of the algorithms I used in TempleOS. So these are the directories. The nothing in temp. Miscellaneous. This is just my test suite. No algorithms. Linux is just that's a A.out or a C program for uncompressing. With my compression format. Okay, so the kernel. So what algorithms are in the kernel? Well, let's see. In the disk, there's a the disk cache is just least recently used, and it has a hash. When you hash the, it takes the block number. Cluster number. It takes the cluster number. No, the block number. It's blocks, not clusters. Takes the block number, and that's the hash. So different partitions will have the same. Will collide, and also aliases of the block number. Anyway, so that's. Now the fat, I learned a lesson from somebody. You want to pick the best fit for the when you're allocating new. You want to pick the best fit for. So you find that you have a. If we do a this is a drive view. This is the fat table, basically. It shows gaps. Anyway, when you allocate a new file, the best strategy is to find the closest fit, the gap that's the closest fit. It makes a big difference. Otherwise, it's not good. So that's a secret I learned there. Of course, there's the Lzw compression. What that does is it's got a table. I think in my case, well, it starts out size starts out 8 bits, 9 bits maybe. Okay, the table entries 00 to FF are. What you do is the table entries, when we add a new entry, let's say we have a file A, B, C, D, C, D, D, C. Okay, so it, I don't remember this exactly, but I think it's you build a chain one more. So we do A, B. So we have one that points. We have an entry that ends in B, and it points to A, which is another table entry. The first 256 table entries are actually it's 12 bits, as a matter of fact. The first 256 entries are actual values. So we put A, B as we have B, and it points back to A, and then we have C, and it points back to B, and then we have C. We have A, B. Well, let's see. D, and it points back to C. And then we have 103. So D, now we have C. So we have D points back to C. No, I think at this point we search. No, hold on a second. D, and it points back to C. C, and it points back to D. C, and it points back to D. At some point what it does is it says, okay, now we have C, C points back to this is a 102 and then a D. This points back to number 102, which is CD, and then we add a D. Do you see how that works? It points to a previous entry, which is a chain, and then it adds one more, and that's how LZW works. Anyway, so I have a Q and a FIFO. There's no real algorithm. It's just linear, no algorithm. My date, I don't think I have any algorithms here. Display editor, no algorithms in the editor. Just a circular doubly linked list with allocated strings for the line of characters. That's the light editor. Exceptions, no algorithms there. Font, no. Okay, this is the most important thing in my operating system. So we have an array. Let's say 4096. It's variable. Or sometimes it's bigger. Sometimes anyway. So we have an array. That's what this is. And what you do is when you have a word you want to add to your symbol table, let's say you want dir, then you take D plus I plus R. What I do is I actually shift it. D shifted over 2, I shifted over 1, R. And then we hack it off. We hack the number so that it's 4096. And then we make a chain, because you can get multiple ones with the same one. We make a chain in a linked list, and this is a hash table linked list. And I have it a little more complicated, since this is I think in reality one of them is 20,000, and so searching that, occasionally you want to search them all, like when finding the address of a function. And it's a little faster if you don't search the empty ones. So I chain together. I have another set of pointers. So that's the most important. Now I have I put different type. I use the same array, and I have different types of entries. I have functions and classes and defines and imports and exports. So I use the same table, but I have different types. Okay, my memory, I have a Malloc. What this is I have an array of, let's say, 1024. Each task has a heap control, and I have an array, let's say like this. But actually what I do is I make it I make it 64 byte. Let's say I have a size, Malloc size 123. What I do is I AND the size with AND tilde D7. So I kill the low. Let's say this. I kill the low bytes, and then this is entry number 120 hex. Anyway, that's just a fancy way of saying I go by eights. Well, why don't I just say that? Yeah, why don't I just say that? I take the number of bytes divided by 8, and that's an array. An array of let's say I don't know what are we left with, 256. I don't know. Anyway, so we have an array of linked lists. This is for the free. This is when you free. I did this backward. I'm sorry. When we malloc, we start with a a chunk of memory and we slice off pieces from the bottom. When we free, we put it in an array of linked lists. It's the same. You might call this a hash table. I don't know. Anyway, an array of linked lists for based on the size. And then when we get a little bit bigger, we take 1024 times n. And then when we get even bigger still, we take 2 to the n. So we have an array for that. We have an array for we have another array, and finally we have another array. An array for big ones, bigger ones, and bigger still. And these are based on each task has a heap control for code and a heap control for data, and those have the linked lists. Multiprocessor psect. This just searches the symbol table linearly for the nearest address. Qsort. Well, I actually was dumbfounded because you want it to be fast for a sorted list. And when I I didn't really study this. I just used it what I had from memory. And so what I did is I pivot around the midpoint of each range. So what you do is I pivot around the midpoint of each range. There's a pivot point, Qsort. I was nice, and I made a special Qsort just for size 64-bit. Most of the time you have pointers, or that's a very common thing, is to have pointers. And so I made a special case for pointers so that we don't do a mem copy. And then I made it even more convenient if you flat out, if that other one was built into the regular Qsort, then I made a non-standard Qsort, which is even faster still, which is integers, and then your comparison is one level less in direction. You don't do pointers to elements. You don't do pointers to elements. You do elements. Anyway, so that's my Qsort. My scheduler. This is just a round robin. Nothing no priorities, just round robin. And if it's sometimes it checks. The tasks are not removed from the queue. They stay in the queue and it just skips them. That's how it works. It just skips over them if they're not ready. And printf, I have string, binary to decimal. I have string. Well, I have some string utilities. Why don't we just make this about? So those are the algorithms in the kernel. I should probably end this video. In the compiler, why don't we make this another video? It's pretty much the same